Cuban. I'll introduce this by saying that when these students approached me to do this project, I was very reluctant and tried to steer them away because this was a very ambitious undertaking for a one-semester project. But it turns out that they proved me wrong and did a pretty nice job on getting this thing working. Dylan, Tori, and Scott.
Well, good morning, everyone, and thank you all so much for joining us here today. Let me first start by introducing myself. My name is Dylan Piernat. These are my partners, Scott Balbach and Victoria Hawkins. We are very excited to share with all of you what we've been strenuously working on throughout this past semester, which, as you can see behind me, is an autonomous guided vehicle. Now, some might wonder, what exactly is an autonomous guided vehicle? An autonomous guided vehicle, or AGV for short, is a mobile robot that follows markers or wires placed on the floor or uses vision, magnets, or lasers for navigation. AGVs are most commonly used in an industrial setting to move various materials around a manufacturing facility. Many different types of AGV applications have increased significantly during the late 20th century, which really sparked our team's interest. Our project was generously sponsored by Nidec Motor Corporation, which is located in Princeton, Indiana. Nidec then created a list of project requirements which had to be strictly followed during the entire course of the project. These requirements for the AGV include a budget of $5,000, use Nidec brushless DC motors and controls for propulsion, limited vehicle dimensions of 2 feet wide by 3.28 feet long and 2 feet tall, capable of following a straight white line of at least 100 feet, carry a 100-pound payload, avoid obstacles or personnel that may enter its path, have one audio and visual alert while in motion, document all performance data, and once the AGV is complete, it's intended to be used at the Nidec Princeton facility to demonstrate its capabilities in an industrial environment. Now I'm going to let Scott explain to you how we started our design.
Our first design issue we had to consider was whether to go with a four-wheel design or a three-wheel design. The four-wheel design allowed for a square base which would accommodate more surface area for the various hardware. The disadvantage, though, was it would require 2 wheels in the back, which would mean more power would be needed to pull those 2 wheels. The three-wheel design would allow for better maneuverability since there would only be a single swivel wheel in the back. This also allowed less resistance against the motors. A disadvantage, though, was there was a non-square base would be needed to accommodate that single swivel wheel. This led us to designing a trapezoidal design, since this would accommodate the most surface area in the center of the AGV and allow for our various hardware to fit on the AGV in the appropriate locations. Shown here in the SOLIDWORKS design we assembled, you can see here that the batteries are placed in the center of the AGV as well as the 100-pound payload. This keeps the center of gravity in the middle of the AGV for stability reasons. Also, you can see the NEMA brackets are located underneath the AGV as well. With the frame fabrication, we developed an AutoCAD layout that fit within Nidec specifications. This allowed us to acquire the top 2 and bottom 2 angles needed to design the trapezoidal shape. This shape was then assembled by utilizing angles that were fabricated in the angles needed to design the trapezoid shape. And then, once that was slid into the square tubing, we were able to bolt them together and had our trapezoidal design. 2 cross members were placed in the center of the AGV to strengthen the AGV and add rigidity. The Nidec motors were attached underneath the frame using a NEMA 34 bracket. 4 bolts were attached to each motor and spacers were used to level the wheels. Wheels were coupled to the gearbox using a hub coupler with a keyway and set screw that was tightened down onto the output shaft. A line following bracket was developed to fit the photo sensors for the navigation of the line to get within the optimal sensing distance, which was 1/8 of an inch. This bracket allowed the sensors to be within that optimal sensing distance while still protecting them from potential damage. The LEDs were placed around the photo sensors to avoid any interference with ambient light while the sensors were trying to get a reading. Here's the completed AGV frame supporting the 100-pound payload, as well as all the hardware needed to be on the AGV. Now I'm going to hand it back over to Dylan to explain the hardware on the AGV.
So once the AGV frame was finished being assembled, it was time to select and install the electrical hardware. The electrical hardware design was very critical due to the fact that every component must be compatible as well as accountable. The motors selected from Nidec are known as their 3.3-inch brushless DC motor series. Some features the team noted and implemented include a 24-volt DC input voltage, power ratings of 1.5 horsepower, NEMA 34 standardized mounting, and speeds of up to 6,000 RPM. With speed capabilities ranging this high, the team decided to take full advantage of a coupled gearbox option having a 10-to-1 gear ratio. This helps add torque while reducing speed at the same time. To control the motors, we use Nidec's newest motor drive, the Green Drive 2.0. Some drive features used for this particular application include analog inputs for motor speed control, digital I/O for motor enable and direction, and a 5-volt DC output powering the LEDs used to create a consistent ambient lighting for our photo sensors. Now, sensors are devices that respond to a physical stimulus such as heat, light, sound, pressure, magnetism, motion, distance, etc., and transmits a resulting impulse for measurement or control purposes. Now, considering this definition, the best sensing methods for this particular AGV application would be distance and light. We chose to use 2 ultrasonic ping sensors mounted like headlights to detect what's in front of the AGV. These require a digital signal to trigger an ultrasonic burst, which is a higher frequency than what humans can hear, and then listens for a return pulse and translates that time into a distance. Then, the line following guidance, we chose SparkFun photo sensors. These sensors output a low voltage when it detects a white or light colored surface, and a high voltage when it detects a dark or black surface. Since this AGV will be used in an industrial setting, visual and audio indicators are required for safety purposes. The team selected an LED stack light to be placed on top of the AGV. The light illuminates green while the AGV is in motion and red while the AGV is stopped. An audio alarm was also selected to remain on while the AGV is in motion, similar to a forklift, and off while the AGV is stopped. Since these indicators both require 24 volts DC to operate, solid-state relays had to be used to separate the circuit. These relays require a digital signal to open or close a switch, which controls whether the indicators are turned on or off. The controller is also known to be the brain of the AGV, which makes it one of the most important hardware components. After extensive research, it was decided to use the National Instruments myRIO controller to control the AGV. Although the controller consists of many other features besides what's listed here, these are some that we decided to implement. 2 analog inputs are used to receive feedback from the photo sensors. 2 analog outputs are used to control the motor speed, and digital I/O lines are used for motor enable and direction, solid-state relays to control the indicators, and feedback from the ping sensors. The controller also has Wi-Fi capabilities, which allows for our programming to communicate wirelessly. A maximum power consumption table was then formulated by adding together the maximum power draw from each hardware component. This allowed for us to figure out what types of batteries were needed for the AGV. We ended up using 2 12-volt deep cycle batteries connected in series, rated at 75 amp hours apiece, to power the motors, green drives, and indicators. Also, we selected a 12-volt lead-acid battery rated at 7 amp hours to power the MyRio controller as well as the ping sensors. 2 separate power circuits were used to isolate and protect the MyRio controller from the potential high current surges the motors might draw. In this block diagram, red is used to indicate power connections, black mechanical connections, and blue input and output connections. So here we have the deep cycle batteries powering the green drives, motors, and indicators, like I mentioned earlier. Although they're not shown in this diagram, we did use 2 15-amp inline fuses to protect each motor drive. The lead-acid battery is powering the MyRio controller and also the ping ultrasonic sensors through a 5-volt voltage regulator. The purpose of this is they require 5 volts to operate. The motors power the LEDs, and the MyRio powers the photosensors with its constant 5-volt output terminal. The photosensors and ultrasonic sensors then feed back data into the MyRio. The MyRio outputs to the solid-state relays and the green drives. Now that the electrical hardware was chosen, electrical connections designed, and finally installed on the frame itself, I'll let Tori explain how we actually got the AGV to operate.
So Nidec uses LabVIEW for lab testing of their products. So to keep the AGV uniform with what the company uses, we decided to also use LabVIEW for programming. LabVIEW has a module created just for the MyRio, as well as FPGA, which stands for Field Programmable Gate Array, and that was utilized for our programming. LabVIEW also generates a human-machine interface, or HMI for short, while the program is being created. HMIs allow us to see what's going on with the AGV while a program is being executed. Using LabVIEW saved us from some budget because no other software or hardware had to be purchased to create an HMI. So our first step of programming was to create the program outline to see what we wanted the AGV to do. From this, we came up with the 3 main subsystems that the AGV controls, which were line following, object detection, and motion indication. The first subsystem, line following, reads analog input from the 2 photocell sensors. It then determines if the contrast is within range. If the contrast is within range, then the motors drive forward. If the contrast is not within range, the motor speed is increased on the respective motor from where the sensor detected it was not within range, until it is once again within the contrast range. For object detection, the controller reads the input from the 2 ultrasonic sensors. If the object is detected too close to the AGV, then the motors will stop. If an object is not detected, then the motors continue running. And the third subsystem, motion indication, is based on whether the motors are running or not. If the motors are on, then the indicators are on, meaning the stack light will be green and the audio alarm is on. If the motors are off, then the indicators will be off, the stack light will be red, and the audio alarm will turn off. Once the program outline was completed, the next step was to create the LabVIEW program. Another benefit to LabVIEW is that the software is set up using block diagrams, much like what our program outlined. LabVIEW is very user-friendly and allows for ease of programming. And now I will show you a few of the main sections of the program. So this is the analog input for the program. These are the analog inputs that are coming from the photocell, and they are compared to a constant number, which we found to be 4 volts. And then if it's less than 4 volts, then the sensors are reading white, and if it's greater than 4 volts, the sensors are reading dark. From there, the program then switches to analog output. And in the analog output, first part is to read the input values from the sensors. And if the sensors are reading white, then the right motor is 0.16 volts, and the left motor will output 0.15 volts to the motors. And the next step is if it is a dark contrast. If the right motor is reading a dark contrast, then the right motor will increase to 0.2 volts, and the left motor will increase to 0.19 volts. These voltages will increase our motor speed enough just to slightly turn the AGV until both photocells are once again on the white line. Once they are once again on the white line, then the motor speed will decrease back to what just the forward trajectory is. And this is our human-machine interface that was generated from the program. This AGV will tell the user if the motors are enabled if the motors are driving forward, as well as the analog output values that are being sent to the motor. It will also tell us the analog input values that are being read from the photocells and if the photocells are seeing a white or a dark contrast. We can also see which indicators are on, any errors that are coming from the controller, and the case that the program is running. Now I will show you a short video of AGV following the line. As you can see in the video, the AGV is supporting the 100-pound payload and is running. Also, the green light is on and the audio alarm is also on. And here you can see that the right photocell is no longer on the right line, so the right motor speed is being increased until both photocells are back again on the white line. And now the photocells no longer see the white line, the motors have stopped, the audio alarm is off, and the indicator has turned red. Now I'm going to go over a few of the most important, okay, so the budget, we were given $5,000 for the budget of the project, and in total we ended up only spending around $2,900, so we ended up saving around $2,000 from our budget. Now I'm going to go over a few of the lessons learned from this project. From the beginning of the design, we knew that producing a bill of materials as soon as possible was necessary in order to compensate for any lead time that we may have on our parts due to shipment. Because we finished the BOM in a timely manner, all the parts came in, giving us enough time to construct the AGV. Also, originally, our first design of the frame only had one crossmember support, but however, when we got the materials in, due to weaker than expected materials, we ended up adding a second crossmember to support all the weight that had to be put on the AGV. We also learned the importance of reading product specifications on data sheets. For example, from the data sheet on the photocell, we discovered how low the photocells needed to be on the white tape, and from this we came up with the line following bracket design. Something else we learned was the importance of checking product compatibility across various platforms. Many sensors on the robotics market are capable with smaller controllers like Raspberry Pis or Arduinos. However, since we were using LabVIEW and a National Instruments controller, we had to make sure that all of the sensors and products we were using were compatible with that one controller. Lastly, we would like to thank some important people for leading us to having such a successful project. First, Robert Pierce United Motor Corporation for their sponsorship, without which this project could not have been capable. Dr. Cuban, our advisor, for giving us guidance and being just as, or not, if more enthusiastic than we were about this project. Dr. Mitchell for organizing this design class. Donna Moore for keeping us all in line throughout the semester and over the last 4 years. And to our professors for their guidance and instructions to give us the tools we needed to complete our education. And lastly, to our parents, friends, and classmates for your support and encouragement through such a demanding project. And that concludes everything we have for you guys today. Are there any questions?
All right, questions? There have to be some questions.
So after this experience, what would you have changed about the motor or the controller that you used? How could it be improved?
Well, we did notice that the motors that we chose were in fact overpowered, so we had to operate at that lower voltage range, as Tori mentioned, 0.15 volts, 0.19 volts roughly. So we could go with smaller motors. As far as control capabilities, we were really satisfied with the MyRio controller, and we would probably keep that the same.
Okay, so you would have reduced probably the speed, so you didn't need to go as fast. Okay, I thought that might be the case, but no problem. Want to make sure you had enough.
Other questions?
I was asked not to ask questions. Future state for a long-term environment and a production environment, did you consider a docking station for recharge for the battery system?
No, we have not considered that yet. It's still such a trial period still that we weren't really considering any long-term stuff as of now, since we're still tweaking all the finishing touches, I guess.
And second question for safety. You have forward sensors. What's the radius of the ultrasonic sensors currently today going in forward motion?
Each of the ultrasonic sensors can see a radius of around 40 degrees for that arc angle, so combined 80 degrees.
And then what about side entry? Someone walking into the side, is there a protection from that?
There is not.
I didn't mean to stump it, it's just things that I've seen happen with these. And you guys did a great job. I want to congratulate you on that first.
Thank you.
Thank you.
Is there any limit to the size of the machine that can be operated like this?
I would say there is some limitation to the size of the machine as to what the voters are capable of hauling. But from what we saw, this AGV could be increased a lot bigger since those voters were way overpowered for this application.
Other questions? I noticed your vehicle's tilted a little bit forward. Was that by design, or is that just the way it worked out?
We went with sort of that design to limit the amount of weight, I guess, on the back wheel, as opposed to it having more of a frontward slope to help have it be dragged along easier in that aspect.
Okay.
So you've got some safety items on there. Do you have an emergency stop anywhere on the unit?
We actually have this switch right here. It'll cut off all power to the AGV, as well as the HMI has a stop button. So at any time, if you hit that stop button, the program will stop executing.
All right. Any other questions? Well, let's give them a hand.